Thank you again for inviting me to this lecture series. This is the second lecture on quantum biology, and last time, I think it was about a month ago or so, we discussed the birth of quantum physics more than 100 years ago. In fact, at the dawn of 20th century, and this was a revolutionary transformation in science, and is still baffling a lot of people's minds, including a lot of physicists. But I think the proof of its correctness is undeniable. And one of the most striking aspects of quantum mechanics is the so-called wave nature of matter. That means that there is nothing really solid about matter at the microscopic level, at least. That is, particles, as we call them, elementary particles, have extended properties. They cannot be localized, and they behave like waves at this level. And this has found, of course, many applications, including X-ray crystallography and electron crystallography. As you can see here, electron microscope showing you a fly, and of course, structure of crystals have been determined by X-ray and electron crystallography and other methods, but these are the most important ones. And probably equally importantly, this allowed us to understand the atomic level construction of molecules and all objects, in fact, all physical matter, starting from elementary particles, building up into atoms and beyond. So in terms of the atomic model, the credit goes to Niels Bohr, and he came up with this so-called planetary model where the electrons orbit the nucleus, which is composed of neutrons and protons, and these orbits are so-called quantized. They have specific energies, of course, and also specific designations, spatial or localization. And the lowest such orbit is called the ground state, and then you have the excited states in a discrete organization. That's actually part of the nomenclature, quantization, quantum physics, that comes from this discrete emergence of energy levels, which normally in classical physics you would not see. But even more importantly than quantization itself, of energy levels, what is emerging from this model is that electrons that actually provides the stability of matter, because in classical physics, electrons, which are negatively charged, would collapse on the positively charged nucleus, with protons being positive, neutrons being neutral, and therefore this kind of rescues the conceptual foundation of our understanding of what atoms are. But on the practical level, the discrete arrangement of electronic spectra, electronic energy levels in atoms and later on in molecules, allows us to basically use these energy level distances between them as some kind of a fingerprint, and this has been used in so-called atomic and molecular spectroscopy. And further applications ensued in fields such as astrophysics, where you can identify by the spectrum of light coming from distant stars what they are composed of in terms of atoms, and also in environmental studies, you can use spectroscopy to determine the concentration of toxins and pollutants and things of this nature. So that's really incredibly important from the applied point of view. And so we are actually now trying to bridge a gap between physics and biology, and so we've seen quantum physics, quantum concepts at work in atoms and molecules, and even large molecules also exhibit discrete spectra of their energy levels. And they become, of course, more and more complicated because they have not only electronic degrees of freedom, but also internal vibrations and rotations, and all of these so-called degrees. The neighboring ones would give you the corresponding wavelength of light. I think I skipped that. There was a formula here. Here it is, which is all important in this connection. Namely, the difference between the two energy levels is equivalent to Planck's constant H and the frequency of electromagnetic radiation. That brings us back to the beginning of quantum physics, namely black body radiation that Planck explained, but it now applies to something really, really close to home, namely transitions between energy states in atoms, and they can be in terms of excitation. So you can use a very specific amount of energy in the form of a quantum of electromagnetic radiation or photon to take one electron from a lower energy level to a higher one, or vice versa. Electrons can spontaneously fall down on an empty available lower energy level and emit photons or quanta of electromagnetic radiation. And many of these would be in the visible spectrum, so you can see that and recognize which energy states and which atom were involved in this. So that's basically how we identify the different, the composition of different substances in terms of atoms and molecules. The same principles apply. Okay, now I said that we're bridging the gap, but however, we don't know exactly where the boundary between classical and quantum physics is, unfortunately. The criterion, which quite often is used in terms of saying, okay, this is cannot be quantum because of the size, basically. So you compare the size of an object to the corresponding quantum wave function wavelength. So remember, in quantum physics, we don't use position and velocity to identify particles, but we instead use the wave function. It's a complex mathematical object with the meaning of related to probability of finding this quantum object somewhere in space at a given point in time, and therefore it has a wavelength as a wave function has a wavelength. So the wavelength is the distance between two neighboring peaks, and the wavelength of a quantum wave function of a particle is given by this formula. It was derived by de Broglie. So it's equal to the Planck constant divided by the momentum p, h over p. H is given, it's a very small number, and p is the momentum, that means mass times velocity. So it's if the mass of an object is very large, then of course this wavelength will be tiny, and then the object with a large mass will have a large size dimension. And this here is an example, a pen cap flying during a boring lesson, and illustrated here is a mass of 5 grams and flies at 0.6 meters per second, and the Planck constant is given. So so you calculate the momentum, mass times v, and divide h over p, and that gives you the hypothetical wavelength of that pen's cap represented as a wave function to be only 10 to the minus 31st meter, which is unimaginably small. Of course, its dimension is by, I forgot, 3 centimeters. D is the size of the cap, 3 centimeters, 0.03 meters. So we're talking about 30 orders of magnitude separation between these two numbers, which is basically ridiculous to say that cap is in a quantum state. All right, so that just gives you a perspective on it. However, and it's not always as simple as that. For example, a nucleic acid in a quantum state? Can it be? Why not? I think it's a large molecule, but it's not huge. It has, for sure, recognizable vibrational, rotational, and electronic states. So it can be in different quantum states. What about amino acids? Same thing, even smaller on average. And then you start putting them together into peptides and peptides into proteins. And to date, I can tell you, I think, well, the latest I've checked, I think the largest protein that has been determined to be in a quantum state is composed of about 100 amino acids. So it's we are getting there in terms of a single biomolecule that can be considered in a quantum state. Just to finish the story, there were some additional experiments that demonstrated quantum nature of the microscopic universe, emphasis on microscopic universe, which showed that this wave-particle duality, where photons were able to collide with electrons and kick them off in a certain direction. So active photons, waves of wave packets of light, behave like particles, like billiard balls. And then I mentioned atomic spectra, molecular spectra, and then double-slit experiments, which is very interesting because they show that seemingly solid objects like electrons and protons, should say not protons and not photons, protons, if allowed to pass through two slits in a barrier, solid barrier, they would go through either one or the other, but experiments show that they go simultaneously through both, and then they recombine at the screen behind, forming a characteristic interference pattern. And the last in these major experiments worth mentioning is the Stern-Gerlach experiment, which determined something completely new, something completely quantum mechanical. There's no equivalent in classical physics, namely the magnetic spin. So electrons and protons and neutrons, they have another property, not just mass, charge, and let's say velocity, but in classical lingo. But they also have a new property, spin, which is quantized as well. That is, it can have either a plus 1/2 or minus 1/2 value. And that's important, actually critically important, because without magnetic spin, there is no magnetism. You cannot explain, I should say, ferromagnetism, which has been known for thousands of years. And I'm sure you've played with with fridge magnets, and these are, strictly speaking, quantum objects, although macroscopic. So, what can we say about quantum theory in essence? Systems exist, quantum systems. We don't know exactly, where this limit is, but I tried to tell you that it could be quite far. Exist in discrete states, could be enumerated, and then it's actually a probabilistic theory, so we never know for sure anything. That kind of shatters the whole philosophical concept of the universe being knowable, predictable. Even a single tiny object like an electron is not knowable completely. We always end up with a probability of something occurring or not occurring. And light is emitted and absorbed from molecules, atoms and other objects that can absorb light as in units of energy called quanta. Okay, so this is a, and then there are some quotes which even some of the greatest minds on this planet express shock at these statements that quantum mechanics is so baffling and so hard to comprehend, because we, I guess, are conditioned as human beings to trust in solidity of objects and predictability of events. All right, and I'll just very quickly go through the postulates of quantum mechanics. I mentioned many times already that the wave function, a complex mathematical object, is the representative property of a system. Call it a state function, describes a state of any system in quantum mechanics, and this is Schrödinger's contribution to quantum physics. And by the way, I don't know if I mentioned, but Schrödinger wrote this amazing book, What is Life, in 1943 or 44, which was about a decade after he got the Nobel Prize in Physics. He ventured into biology and posed a lot of questions which are even today relevant. So he described a method of finding the evolution of the system, but not this deterministically, but probabilistically, which is called the Schrödinger equation. I will maybe skip these specific properties of the wave functions that describe quantum systems. Are not just arbitrary functions. They need to satisfy some properties, because the square of such a function must be a probability. Probabilities must be greater than or equal than 0 and less or equal than 1. So, and they have to add up to unity when you sum over all space. That has to be so-called normalized. So these are the properties. They have to be integrable, and it's a lot of mathematical complexity, which I guess for you guys is not necessary to know, but it's important to keep in mind that these things are incredibly well classified and codified. So this is one of the most beautiful and most elegant theories of that physics has produced. So the square of this the wave function psi is the probability of this object being in given place and given time. Now this was the third postulate here, which is kind of difficult to explain in simple terms. I'll just say that we replaced solidity of objects by wave functions, kind of squishy probability distributions and now we're replacing things that in classical physics could be easily measured, like position and velocity or momentum, energy, angular momentum, and things of this nature with so-called Hermitian operators. These operators act on wave functions and return when they act on the wave function. As you can see here, some of them are differential operators, some are just functions. They return the so-called eigenvalue. That means the expected amount of the quantity times the wave function itself. Okay, I'll move on. And this is the crowning achievement of Schrödinger in 1926, and then 1933 Nobel Prize for this. Seems like a complicated equation. It really is the equivalence of Newton's equation in classical physics translated into quantum physics. And what you have here is on the right hand side is this time derivative of the wave function. So that's evolution on the right hand side, di psi, di t. this curly symbol looks like D. We call it die in physics, in mathematics. It's a derivative with respect to time, so it shows you how the wave function changes over time. And on the left-hand side, you have the operator acting on it. It's the second derivative with respect to x. It's in quantum mechanics kinetic energy. If you remember high school physics, or if you ever took college physics, you would probably recall that kinetic energy is mass times velocity squared divided by 2. I guess if I showed you this and didn't tell you that's kinetic energy, you wouldn't know. It's h bar squared divided by 2m di squared di x squared. That's kinetic energy, and then there's potential energy. So any quantum object particle will experience movement, and kinetic energy describes movement, and also some potentials generated externally, let's say electrostatic potential, gravitational potential, or chemical potentials. And then you solve this equation and obtain how the wave function changes and evolves over space and time, and that gives you the probability of it moving to some place. So this is as good as it gets. Maybe for you it's not very satisfying because it doesn't really have something you can hold on to, but trust me, this has been used to our advantage technologically. Because of this we can solve the behavior of electrons in semiconductors, and we can understand the superconductivity and things of this nature. So it's very useful, but it's very technical, so it's very difficult to explain in precise terms. And when you have now, so far we've been talking about a single particle in some kind of general environment. This function here, h, is the Hamiltonian. So this is the energy function. There is a formula developed by Paul Dirac, and he got the Nobel Prize in 1933 with Schrödinger. A very elegant, simpler than these equations I showed you, but would be too time-consuming if I went into details of this. What I'm trying to say now is that we can extend all of this into a system of arbitrary number of particles or quantum objects, and simply by adding all their kinetic energies and all their potential energies, as well as interaction energies between them. So this is an example of how you would solve the or formulate. Solving is something else. It would take a long time to solve it, but to formulate the problem of electrons in atoms, you'd have to add up all the electronic energies as they orbit around the nucleus and then interact with the nucleus. So that's in V, minus Z E squared over Ri. This is Ri is the distance to the center of the nucleus. Z is the number of atomic number, the number of protons, and E squared electronic charge squared. And then sum over pairs Ij, that means sum over all the electron-electron interactions, however many you have. And this is the Hamiltonian, which you then solve the Schrödinger equation for. There are many techniques, highly mathematical, but really well developed in the 60s and 70s for not only atoms, but also complex molecules. Okay, so that gets kind of hairy. If you want to study atomic molecular physics or quantum chemistry, you need to know it. And this is the key. So now we have a methodology to understand the building of the physical matter all the way from nuclear matter to atomic to molecular and now to chemistry. And in fact, I mentioned this. In fact, in chemistry, two things are necessary from the quantum physics point of view to understand chemistry. The first one is the spin. I mentioned to you already, without the presence of spin, you cannot understand the periodic table of elements by Mendeleev because of the occupation numbers of the atomic orbitals. And these are electrons or fermions. They have half-integer spin. What that means that these electrons do not allow another spin to occupy the same state. But the state means energy, angular momentum, and spin. So spin gives you the, for example, if you know a little bit about this, the lowest energy state for hydrogen is 1s. So there are two electrons in 1s, which one has spin up and the other spin down. Okay, so there is no magnetism without spin, I mentioned. There is no Mendeleev's table of element without spin. And then the second thing, I will just stay here and then come back to spin. The second thing that chemistry requires is chemical bonds, because you bring atoms to form molecules. Now, there is no chemical bond without quantum mechanics because you require electrons. You either have covalent bonds where electrons are shared, and these are really wave functions. So these cloudy things which are now in covalent bonds localized between two atoms. And the second possibility is ionic bonds where electrons hop from or jump from one atom to another, forming a charged attraction between them, like sodium chloride salt, and that is also a quantum transition. So chemistry cannot be comprehended without quantum physics, which probably is not sufficiently publicized, but chemists know it. Anyway, back to spin. I mentioned to you that there are two types of quantum particles, bosons and fermions. And fermions are like electrons, which do not allow other fermions to occupy the same state. Bosons, on the other hand, don't care. You can have as many bosons in the same state as you want. And one example of bosons is photons. So the electromagnetic wave is a boson. So you can have as many photons or quanta of light with the same wavelength or frequency as you want. And that's important as well, because that leads to our understanding of things like laser action, which is a quantum process, and so on. Now, there are some other quantum so-called quasi-particles I'll just mention here. So lattice vibrations, which is important, are called phonons. Spin and lattice are called magnons, and so on. So that's another step which I just don't want you to think that I'm trying to cover too much, but this is an important idea which brings us closer to biology, surprisingly, because these quantum excitations exist in solid objects and macroscopic, in fact. So crystals, all crystals, when you analyze their dynamics with spectroscopy or even colorimetry, the same with the analysis of magnets or complex materials, you will find as properties such as spectral lines or absorption characteristics or specific heats, you will find the underlying quantum interactions. And that's very important, because now I want to emphasize something which I think in quantum biology has been almost completely missed. We'll come to it probably on Thursday, and not today, but I just want to advertise this aspect early, namely, almost all quantum biology today is kind of focused on one aspect, namely, single particle property in the biological system, like photosynthesis, that there is a quantum transition taking place where the electron is excited and then de-excited and triggers something else. But I believe that the future of quantum biology lies in understanding the connection, not necessarily to the elementary particle type of quantum physics, but to solid state physics, because these are microscopic systems, and biological systems are systems of huge numbers of particles, just like these solid state systems like crystals and magnets and lasers and so on. So very briefly, this is where these hallmarks of quantum behavior can be manifested in subtle ways, as are for the two types of quantum systems: the fermions, or Fermi-Dirac particles with spin 1/2, and Bose-Einstein particles with integer spin, like photons. And as you can see here, the Fermi-Dirac, you can only put one red dot, one particle at one level. For Bose-Einstein, you can put as many as you want at the ground state or any other state. And then you have in the green, you have the sort of classical Maxwell-Gibbs-Boltzmann distribution, which is basically saying to you that the higher the energy, the lower the probability of having a particle found there. So you can distinguish very clearly, as you can see here, although it's a cartoon, that the green is how you would see a classical system of 6 particles distribute itself among some number of energy levels, as opposed to the Fermi-Dirac quantum system in red, as opposed to Bose-Einstein in blue. So that's where you, in my opinion, you will find richness of quantum biology in the future. And to my knowledge, not many people are looking at this kind of property. Okay, so I'll skip this. The Bose-Einstein story is quite interesting. Bose, an Indian genius physicist, and he came up with this notion of Bose-Einstein. Now it's called Bose-Einstein statistics of distribution, probability distribution. They couldn't get it published. I guess there was a lot of biases in the scientific literature at the time, as there are today. And the paper was translated by Einstein, got accepted immediately, and well, Einstein got a Nobel Prize, not for this paper, and Bose didn't get a Nobel Prize, but he was nominated, but became a fellow of the Royal Society, big honor, without a PhD. That's quite an amazing story. You should read about him. Okay, so these are some mathematical formulas between the two probability distributions. Let's skip it. It shows you the occupation of energy levels for fermions as a function of energy along the x-axis, and the probability on the y-axis of being in an energy state at different temperatures. So these kinds of characteristic plots would lead to the recognition that some systems are in a quantum mode, and that's a comparison between the probability of being in a given energy state for the 3 types of behaviors. The quantum Fermi-Dirac is at the bottom, the quantum Bose-Einstein is at the top, and the classical is in the middle. So once you have the probability, I don't know, probably none of you studied statistical physics, but once you have this kind of function, the probability distribution function, you can calculate pretty much every thermodynamic property, including specific heat susceptibilities and so on. So that's, in my opinion, a very clear path forward in trying to search for quantum manifestations in biology. Okay, we already know that there are macroscopic quantum effects in physics, and this is a short list. Superconductivity, I'm sure you heard about it. In other words, materials conducting current without any resistance, any losses. Superfluidity, materials which don't offer any viscosity, non-viscous, so you can twirl it and create a vortex that never stops. A laser action, you have scanners, of course, QR codes and barcodes and everything else like that. It's based on laser action, which is a quantum process. And I guess I'm sure that the cashiers at Safeway do not realize that they're operating a quantum machine. And then crystal vibrations, phonons. This is where actually, I'll come back to it. Actually, Einstein made an error, conceptual mistake. There was another puzzle like black body radiation. Then semiconductors, we all know about semiconductor electronics everywhere. This is also based on principles of tunneling. Electrons can tunnel. I mentioned, I guess, to you, this is one of the hallmarks of quantum physics. And magnetism, fridge magnets, all of that is also quantum. At the base, of course, quantum physics didn't stop at that point. It continued into deeper and more exotic, I guess, esoteric realms. And now we talk about the standard models, understanding all of forces in nature at the lowest level. The only thing that is still missing is gravity. And that was Einstein's obsession. Nobody has been able to incorporate gravitational forces into quantum physics. And we know that gravity is, of course, important in biology, but it's a very weak force, and it really matters only on the kind of cosmic scale in terms of interactions between objects. All the interactions in biology are overwhelmingly larger, like, chemical bonds or dielectric interactions or electrostatic interactions, much stronger than gravity. So now, what is the take-home lesson from all of this in terms of what quantum mechanics can offer to our understanding of living nature, living systems? Well, I mentioned the stability of electrons in atoms. There would be no atoms, then the electrons would collapse on the nucleus. So that means we can construct the building blocks of natural systems from elementary particles, electron, proton, neutrons, to atoms, from atoms to molecules, from molecules to macromolecules, and then you go to biochemistry with nucleic acids, amino acids, phospholipids, sugars, and so on, and you start building the components of a living cell. And then from that, you build multicellular organisms and so on. Now, quantum mechanics also provides a high level of complexity out of simple symmetries, such as atoms within planetary-like model becoming really complex when you add a lot of electrons. So we quickly generate very interesting, intriguing structures. And the most interesting things for you, maybe for biology in general, are the next two or three, namely entanglement, which I didn't spend much time on, but entanglement means that two or more quantum elements, elementary particles or photons or some other individual elements, when put together and prepared in a specific state, they stay in principle connected, irrespective of the distance between them. So they're entangled, and that's kind of spooky. And in fact, Einstein used this term spooky action at a distance. That is, you can then remove one or both of these entangled pieces to the end of the galaxy, one and the other to the opposite end, and they are still in a tight connected state. So if you test the property, they measure the state of, let's say, particle A, particle B, will be found exactly in the prepared state, let's say opposite spin. So how does it happen? You know, we know that physics, according to Einstein, against special relativity, mass or signals cannot travel faster than the speed of light, and so that's kind of contradictory. I recently read a very interesting article commenting on the fact that there might be an explanation which actually saves causality, and it involves communication back in time to the point that they were in the same point in space, and then communicating to the other particle what its state must be when the first particle state is measured. Anyway, that's kind of far-fetched. I don't think we need travel back in time in biology, but entanglement is interesting from another point of view, namely the synchronization, I should say, not synchronicity, something else, synchronization of a huge number of independent processes in biological systems, which is, in my opinion, maybe the central enigma of biology, how an organism functions as an organism, not as a bag of molecules. Perhaps there are quantum correlations. And coherence, it means that there is a single unitary state, like in laser. You know, you see a single color of light coming from the laser. Perhaps in a different version of it, you could consider our functioning of the brain to be some kind of coherent state of the mind. And then there is the question of information, quantum information storage and processing, how the memory works, how the brain works, how we can, some of us at least, rapidly solve some complex equations or mathematical formulas. Maybe it's by quantum computing. This actually is not such a far-fetched idea. There's a lot of papers on this, that quantum computing, quantum information is part and parcel of the functioning of the brain. And then the next one is stochasticity. In other words, the biological systems are not completely predictable. They have built-in uncertainties. So that's consistent with quantum theory, but not necessarily the only way of explaining it. And then I mentioned quantum statistics, and finally tunneling. And this is important at the kind of microscopic level of quantum functioning. Many reactions are almost improbable or impossible to accomplish unless there is some tunneling taking place. In other words, forbidden pathways, forbidden routes for electron transfer classically become possible quantum mechanically if the wavelength of that particle is longer than the barrier that it has to overcome. So I mentioned solids as an important part of quantum physics, where also quantization is part and parcel of, for example, crystal dynamics, and we also have, in this case, omega is not the frequency of light, but the frequency of phonons or lattice vibrations. So this was known in about 1930 or so, that there were different types of specific heat values for different temperatures of crystals, and there was Einstein assumed that atoms and molecules forming a solid, a crystal, vibrate at the same frequency, but they are not correlated, and that ended up with incorrect low temperature behavior. Debye actually assumed that instead there are, I'm sorry, I have to stop for a second. My apology, I'm still recovering from a flu. So what I was going to say is that Debye assumed that there are waves in solids which propagate and carry quanta of energy, just like photons carry quanta of electromagnetic energy. Debye assumed phonons, so photons, electromagnetic phonons, mechanical waves, still quantized. And that's something that I'll come back to on Thursday, because there is a model fashioned after Debye's model to explain human metabolism and animal metabolism using very similar concept. So keep in mind that quantum physics is not just electrons and protons and neutrons, but it's also quantization of energy in complex systems, large systems, such as crystals. And this is a list of technological achievements that were afforded by quantum physics, consumer electronic computers, laser scanners, spectroscopy, MRI, NMR, atomic clocks, GPS, X-rays, solar batteries, based on photoelectric principles, of course, photosensors, photodetectors, PET scans. So now we are in the next few minutes, we'll be looking at how we breach this gap between physics and biology. We already, this is a hierarchical organization of matter, starting from quarks to the bottom, from quarks to elementary particles, to nuclei, to atoms, to molecules. And that's all pretty much standard quantum physics. You know, we know pretty much everything here, how to calculate and do it exactly, or with great precision. Now we go up in scale. So what is the scale now? A molecule, macromolecule, where we still can use quantum principles, would be something on the order of a nanometer. I mentioned to you this large protein, not large, but a protein with the largest protein with a quantum state determined recently. So about a nanometer, 10 to the minus 9th, still very small, right? It is not something that you can touch and see under the naked eye. So what do? Well, we now go to biomolecules, which would have like thousands of atoms, and things get complicated. Quantum chemistry. So the state of the art here is as you build bigger and bigger molecules, biomolecules, you kind of compromise a bit. And a large chunk of it can be done classically, but some sensitive parts like receptors or catalytic sites represent quantum physically or chemically, same thing. In other words, you now say that not the entire molecule biomolecule is in a quantum state, but a part of it maybe. And maybe that's where the recognition between other molecules binding with ligands occurs. We'll come back to it when we talk about the sense of smell, for example, or vision. So, the compromise that I also kind of agree with is reasonable here, because we are not saying that, all the classical physics is nonsense. Everything has to be solved by quantum equations like Schrödinger's equation. No, but what we are saying is that by and large, a lot of what we know is explainable classically, but some subtle things can be much better understood if we involve quantum physics or quantum chemistry. So this is the mesoscale. This is probably the playground of quantum biology of the future, where we'll better understand, for example, let's start with something reasonably simple, like a virus or a bacterium or a single cell. How do these objects behave the way they do in a quite often very intelligent way, or very dedicated and efficient? So one of the properties of quantum physics is great efficiency of these processes. Now, beyond that, so far, at the level of organisms, we use mechanics and thermodynamics and these kinds of, and of course, morphological analyses, but nothing really as sophisticated as quantum physics. Now, what I want to bring to your attention is also the scales that need to be borne in mind, because it matters. I mentioned to you that the Broglie principle, the size of the wavelength compared to the size of the object, and you can see here how we go on the object scale with size, and with electrons, femtometer, that's 10 to the minus 15th, proton 0.8 femtometer, neutron. Then you have the hydrogen, it's 0.5 angstroms, hydrogen bond 0.3 nanometers, carbon, and so on. So we are building the blocks. We go to the cells, and the smallest cells would be prokaryotic, let's say fraction of a micrometer. I typically think of cells as starting from E. coli about micrometer to eukaryotic, which are actually tens of micrometers, starting with 10 maybe. And then you have the number of atoms, powers of 10 for cells, 10 to the 10th, 10 to the 13th. And so that, if you look at a single cell, the size is, so 10 micrometers, 10 to the minus 5th meters, compared to the hydrogen atom, 10 to the minus 10, 100,000 times larger than the hydrogen. And of course, we solved hydrogen quantum mechanically. Can we solve the cell quantum mechanically? Probably not in our lifetime. But more importantly is the complexity and organization. So, of course, cells have many different parts. And maybe for this reason, we have to focus on aspects of the cell where the quantum effects are the most likely to take place. That's another representation of the same thing. Here you see not only the comparison between different sizes, starting from, again, hydrogen, DNA, you see down there, carbon buckyball, ribosomes, 20 by 30 nanometers, viruses, they can be up to 100 nanometers. That's quite, it looks like a coronavirus to me, but maybe not COVID because the slide is older than that. Then we have E. coli, see, red blood cells, hair, 0.1 milli, so at 100 nanometers, the thickness of a single hair, then ants, and then humans. But up above, and this is important because it tells you what we can and cannot probe easily for such properties as quantum energy levels. You have to compare to it the wavelength of corresponding probes, which typically involve some electromagnetic radiation. So soft X-rays cover the range of angstroms to nanometers. Ultraviolet tends to maybe tens of micrometers. Infrared, you have 10 to the minus 4 to 10 to the minus 6 meters. Microwave up to more than a millimeter. And then we stop. We're visible, but that's kind of observation. This will not give us any fine detail. So this, and one more time, sorry, pay attention to the top numbers, a list of numbers. So we are ranging here from, let's say, an angstrom or below to, let's say, giraffe or elephant, 10 meters. So biological scale in terms of size compared to the component size, we have 11, 12 orders of magnitude in dimensions to consider. That's enormous. This is a similar representation for time scales of different processes. The biological time scales ranging from, that's even more mind-boggling, from actually at the left end of the scale, we are missing some numbers. So it's a chemical bond vibrations are very rapid. It's less than a picosecond, 10 to the minus 12 seconds. So these bonds vibrate, shake a lot all the time. And then you have diffusion, cell signaling ranging from microseconds to tens of milliseconds. And then you have deliberate acts, operations from hundreds of milliseconds. That's human response time, less than a second. And then, of course, you have the human lifespan. That's about 1 billion seconds, 3 billion, if I remember correctly, if you count the number of years and seconds. And then, of course, you have the time span of life on Earth, which is about 4 billion years. So, and it's, by the way, not trivial, because it's life on Earth is a single experiment. We haven't been able to synthetically create new life. It's only life from life. Not quite sure how it started, but it continues, luckily. And so when you look at these scales, and I will take picoseconds as the beginning of it, not 10 to the minus 7th, picoseconds to 10 to the 17th. If you want to simulate all life on the planet over time, that there will be 29 orders of magnitude. It's huge. It's impossible, okay, for now. And I will probably finish, let's see. Yeah, I will finish with the next slide, but mention also, this is very important from the point of view of where and in what sort of range of our energies we can find quantum effects in biology at a more significant level than just, chemistry, because as you will see on Thursday, quantum biology is not interested in so-called trivial or obvious quantum effects in biological systems, like, every chemical bond is quantum, so what? But nonetheless, we need to understand the energy levels, and this is a list of these, which is also translated into the affinity scale, which biochemists and cell biologists use, the values of KDs. So covalent bonds, very strong, 90 kilocalories per mole, distances 1.5 angstroms, and then you can go down the list. And I just want to bring to your attention two things which are absolutely crucial to biology, to understand biology from the physics point of view. Number one is this KT, that means thermal energy, because living systems exist, and humans especially, at very narrow range of temperatures. They can exist, humans, a human body at about 36.6, 37 degrees Celsius. So this KT is available to every degree of freedom abundantly. So 0.6 kilocalories per mole is a cutoff. In other words, anything that has less energy than this is noise. So you don't have, if you find an effect which is 0.3 kilocalories per mole, you could say, well, yeah, that's probably just random noise. And the last thing is biological energy. We talked about quantization of energy in physics as an important hallmark of quantum physics. Here we actually have the first evidence that biology is quantum, because pretty much, I don't know, 99% probably of all usable energy in biological systems is in the form of GTP, or mainly ATP, energy-giving molecules, especially ATP and then GTP. And that's what I call biological energy quanta. And they come in units. It's let's say one step of a kinesin motor protein on microtubules costs 1 molecule of ATP. Muscle contraction, motor protein movement, ATPases, enzymatic catalysis, all of these things, or even DNA transcription and translation to encode a single amino acid. It costs, I don't remember exactly, but probably about 4 ATP molecules for the production of it, transcription, translation, and so on. There is a range depending whether you use GTP or ATP and what concentrations are, but that's the range of characteristic range of biological quanta of energy, depending on which molecule you use. But it is a quantum. It could be a quantum of 3 kilocalories per mole in the lowest amount, or 60. Okay, so we've come to this realization that maybe building the biological universe from elementary particles through condensed physics and chemistry and biochemistry to biology in a nice linear fashion is a bit futile, because each of these fields has its own elements and the rules of the game. But nonetheless, the one field below should not be violated by any novel rules that emerge at the higher level. So in a way, biological quantum biology should be respecting the rules of physics and rules of chemistry and biochemistry and so on. And that's where we will go. I guess we have to stop now.
Yeah, great.
I again apologize for the break, but anyway.
Yeah, so we'll continue on Thursday, and thanks very much for today. Yeah, so we'll keep on going. Okay.
Thank you.
Great.
And if anybody has any questions, please email me. I'll be happy to respond.
Right. Great. Okay. Thank you.